too high. Okay. Yes. So, but even though there is a lot of good promise about the servlet that you don't need to manage the server, but the reality is not that simple. One thing is these days there is so many cloud service model. So the servlet abstract only the small part of your application that is a computation. But here is cloud service model. It seems like a lot, but it's actually like a lot more, which is like here is just a part of it. So you can see that in the reality there is so many fragmented tool chain that you need to like glue them together to develop the application. And the core part of it is your data, but the servlet model not encapsulate that. So you basically you need manual integration between them. Like let's say you need to have some state management and then have a servlet function to glue them everything. And it's quite steep learning curve as well, since that we have so many services and we have a lot of people. It's almost impossible to know all, but still people usually like just learn some of them. And another thing is about the well-known problem on the servlet. So it is a cold start. For some people don't know, cold start, it means so when the servlet need to run something, but there is not enough resource, so it need to allocate the resource on the file. So at the time that it need to allocate the first resource, it usually take really long. So that's why we call cold start. So and the last is limited stateful handling. So with as I mentioned, servlet is completely like focused on the computation, like you write the function, but it completely stateless. So if you want to have some kind of stateful, you literally work around somehow like using the cloud storage or something. So we also did more than just literature review. So we have done some survey. I believe, even though we call survey, but it is a regional ICOP that we start before doing the national ICOP. So in this program, we have interviewed 21 practitioners across the domain, and most of them just report that developing and maintaining the application is still a main pain point, and cost is just a small part of it. And for what they expect, they want to have like some solution that have like quality and simplicity, something that make them work faster, easier, and the cost is just a fraction of it. So basically, the idea is they want to have some higher abstraction that make them more productive, while still maintaining the performance that they can achieve with a lower abstraction. So let's go deeper into the technical root cause of why they talk about the complexity. So there is so many of them. First, let's look into my use case example. So in this use case, you can see that it is some kind of like workflow using a multiple function to process the video. And I just want you to focus that in each state of the function, since the function is only manage the computation, so you still need some form of the staging storage to hold the data, intermediate data. So which make it quite burden and have like more work for the developer. And then to make this workflow, you have a multiple option, but one of them using a workflow orchestrator. But you just see that, okay, even though you have a workflow orchestrator to orchestrate the like task to task invocation, but you realize that the logic of the the data it's not just about the workflow orchestrator alone. It has the flow of data as well. So in the end, developers still need to manage the data flow between each step. So, and the next part is about the deployment problem. That okay, as I mentioned again and again, that function and the state is separate. So sure that development like experience of developer gonna be go down. But the thing is, it's limited how much you can achieve as a performance as well, because you cannot control like where is the location of the function. I mean, you can control, but the granular is quite big. Like you cannot control the specific location inside the data center in the cloud. So, and we have done some preliminary experiment that, so if the function and the data is far apart, like over multiple data center, which is usually happen because it's a recommended way to configure the servlet in that way to have like high availability. So you're gonna have like extremely high latency. And alternatively, in the base case, you can deploy a function and the data in the same machine, same host machine, which can be like 35 times faster. So the next is so now we want to fine tune because we have some non-functional requirement. It could be like QoS, it could be some kind of constraint, and the fine tuning objective for us as a developer and for the people that work on the cloud is completely counterproductive. So what happened is in the developer, you want to optimize for the meeting the SLO, like make function run faster or reducing the cost. But as the objective for cloud provider, they want to optimize for resource utilization by reducing the cost of the hardware. By doing that, they need to oversubscription, which it can make your function run slower. Lastly, so the parameter that the cloud provider give us still be something like CPU and memory utilization or the concurrency control that quite primitive. So basically, you don't know like, what you're gonna get by this parameter. So what you need to do, you need to do multiple round of trial and error. And this complexity is just go beyond when we need to deploy in the edge cloud deployment. So as you know that IoT become a thing right now, and people start thinking about like deploy the service close to the user to optimize for the performance. And we can see that there is some part that is latency tolerance and latency sensitive. So the idea is we want to deploy the latency sensitive code to the user by deploying it to the cloud. Because if we deploy it to so if we deploy both of function to the cloud, the latency is going to be like really high because of the network latency. But if we deploy to the edge, it's much faster. But the thing is, there is much more component for the developer or like operator that they need to manage and maintain. So the basically complexity is just go much higher. And if they don't manage it properly, since it's not like the whole system is not just in single data center anymore, a lot of things can go wrong. One example is a network partition. So since this is not a reliable link, and when the network partition happen, so data can be asynchronous, and it just like make your function invalid or maybe like not operate at all. So to solve all the problem, I have done to the 3 stages of the work. So first of all, we have some idea that okay, since everything become fragmented, so how we can become like unify everything into the single platform, and then everything becomes a single platform, sure, and the development productivity go a bit better, but still there is some deployment problem that okay, so if they need to optimize for the QoS SLA, so they still need to do multiple rounds of fine tuning. So and now we see that okay, we unify everything to the single platform. It seems that we can somehow enforce this by automation, because like everything previously is almost like impossible because everything becomes like fragmented. if you want to automate it, it needs to be automated at the cloud level, and everything is just limited by what they give you. And lastly, we think that how to extend this platform to the edge cloud deployment. So we come up with the IoT extension that we call as the OS IoT, which basically it adds the element of distributed coordination. So let's start with the first paradigm, OS paradigm that we are talking about. So let's compare it between fast and OS. So we have three main challenge in here that, okay, first of all, it's separate the state and the data, the computation and the data is separate. So now we want to abstract everything into the single unified platform. And the parameter that for fine tuning for the performance is the primitive in the fast. But on the OS, we want it to be high level, something like just like, okay, how many throughput user want? So now it's tied to the application and the user get what they want. Like let's say they want 10,000 requests per second, or they want object, function and data to be co-located together. So basically just specify what they want in the high level way. And now the parameter is not counterproductive anymore because user just explain what they want, exactly what they want. And as a cloud provider or a system, as a system side, we know that this is what the developer want. So the goal of optimization is completely down here of the line. So, and let's say that, okay, what is gonna be like abstraction or like development flow that provided by OS. So you can see that in fast, we still need to write like everything step by step, application logic and workflow definition, and everything just go to the completely different tool chain. For the OS, everything just go to the single unified platform. And to develop this, it basically not change much for on like how we usually do in the like Kubernetes or like function as a service. So we just write a code and package it into the containerization with something like Docker. You can use like Podman. It just like the idea is just using the container image, and then we write some kind of like deployment configuration. So in the fast, you need to write a lot of configuration file to matching to each tool. But in OS, everything you define in just like single class definition, and then we deploy them. And ideally, we can create a distributed class runtime inside here, but we could talk about like how it happened. So the interface is that we design is a YAML file. In case you don't know, I believe that most of people know about JSON. So YAML file is just another form of JSON that more human friendly. It is like key value, and then you can nest that the key value. So in here we can see that there is two classes. One is an image and one is a label image. So and there is a state. So one is like state, which is the image, and another one is a label data. So you can see that we just define the function, and inside the function and the class, we can specify the non-functional requirement as like QoS, like availability, throughput, or something. So, and since we want to enforce that non-functional requirement, one thing that we realize that if we have a single static runtime design, it kind of like complicate, like because we cannot just use a single static runtime to optimize all the optimization goal. Like for example, like okay, if the cost sensitive app, we need to optimize by minimizing the caching to like reduce the memory usage. But for latency critical app, we want to act more aggressive caching because caching can, like shorten down the latency by a lot. So we need to add more component that we call as a template. So basically, template each separate template can generate the new runtime. So now the runtime is not static; it can be like dynamic. So and then the system should do some kind of like matchmaker to matching between the template and class definition to create a new deployment. So how to do this? So we create a architecture for the OS that we have a package manager that accepts the deployment package from the developer, and then it's sent to the class runtime manager that basically deploy on the different type of the system. So with this, we can use some kind of like orchestrator, or like it could be like just cloud API to deploy the real class runtime out of it. And in this class runtime manager, the idea is the system provider or like platform provider, they just decide the template that work based on their system. And one of the example that we can show is LTAG template that come from the latency, throughput, availability guarantee. So since we just start off this work, we cannot like do it through all the combination of the SLA. Yes, we just focus on the 3 parameters, that latency, throughput, and availability. Sorry, not our latency, it is locality. So this what you see now is a class runtime. So what is mean the class runtime? So basically you write the application and deploy it as a function. So you need to have like some kind of like runtime to run your class. And in here we have like 3 main components: invoker, storage, and then function. So basically function is the same as the fast function, that it basically auto scaling, that you can scale it out to handle more workload. And then we have a persistent storage that we can use it to keep the state of the data. And we have the distributed hash table that I don't want to go too deep on detail, but you can imagine that it's some kind of like hash table that work across of the system. And we can use some kind of like hashing mechanism that we can optimize for the data locality by routing the request into the target object.
What does LTAG represent here?
Locality, throughput, availability guarantee. So how we do the NFR enforcement? So we have the function. So basically that represents how the function gonna run. So if we want to enforce the throughput, we want to guarantee the availability of the resource that we want to pre-allocate based on the demand of the workload. So let's say that they want a 10,000 requests per second. So we need to calculate how many replica of the function that we need to use that can meet the requirement. So in this case, we basically just do some kind of monitoring and then like adaptive resource to meet the requirement. And the next is locality enforcement. Since now we have everything into the single platform, and we have a distributed hash table. So basically, in the first deployment, we can, if the user specify that they want everything to be in the single machine or like low quality, so we can just deploy in this layer to meet the locality. And then so next thing is we have a hashing mechanism that can allow the request to the object that is getting deployed. So in that way, it basically don't need to go the multiple hop and like come and guessing where is the object is. And to enforce the availability, basically we just use standard pattern that is we call as a primary replica with the automatic failover. So basically, you can imagine that if this component down, there is still another component that hold a copy of the data. And when we call it primary replica, so only one object is gonna be active at the time. So when you have a read and write, going to go just one object. But when the one mode fail, the system automatically recognize and then make the copy become a primary. and to calculate like, how many copy to meet the availability requirement. So there is a lot of work that already done on this. This one is a simple formula that we use since we don't use I mean in the current state we don't use any sophisticated consistency or like consensus protocol yet. So we can just simply use really simple like multiply calculate based on p number. So p number is the baseline availability of a single machine. So if like, let's say if the machine down within like let's say 10% at a time, so the p number gonna be like 0.9, and then you calculate given the a like let's say the target is 99.999 availability. So you can calculate it, and then you're gonna get the end value. And I believe that with the example that I just mentioned, it's gonna be 4. So we have done some evaluation to see like how well this thing go and how much we can achieve by doing this enforcement. So we have a 4 baseline. One is a Knative, and we have a 2. By the way, I forgot to mention, Upalaka is OS implementation in this current state of the world. So we have another name, which I'm gonna mention it later. So we have a 2 version of Upalaka with the different non-functional requirement that's specified by developer. One is a local, and next is a local with warm. Warm is mean they define some level of throughput requirement that they want to meet. And then the ideal, you can imagine that, okay, if everything is just a single large machine and you can deploy in, with a limited resource in the Knative way. So, and we can see that with the simply like deploy the thing in the single machine, you can achieve like either 1.4 times with the baseline of the chatty, and with data intensive, you can achieve up to 4 times lower latency. And then with the bursty workload, you can imagine that, okay, in the case of Knative, it need to scale up and down like again and again. So the cold start gonna happen a lot, and it cause system slow down because it need to reserve a new resource. But when we already probably define how much they want, everything become a warm invocation, and we can achieve up to like 46 times. And this can be achieved by basically, you can just give the system non-functional requirement, and Upalaka can just automatically configure to meet the non-functional. You don't need to do the manual refinement like compared to Knative. So you can think that, okay, you can achieve the same thing with the fast, you have enough level of control. But in OAS or Upalaka, everything is automatic. So, and to achieve the target availability, as I mentioned, so we also do the experiment to see how well this thing go. And in this experiment, we inject the failure in every 3 minutes or 180 seconds. So which means that you're gonna have a baseline allow 9.4 availability time if you do nothing. So, and here we have a multiple target availability like 99, 99.9, 99.99, 99.999, which means that we're gonna have like some target that request should be able to serve at the time. So, and we can see that the result is always a bit lower, and the replica is like linearly scaling. So we can see that the system can enforce the availability with the light side resource. So if you do it by the hand, so you need to do a lot of experiment to see that, okay, this is exactly the least amount of resource that you need. But as since you are a developer, there is some, level number of the performance availability baseline on the system side that it's hard for you to know, and you cannot do much of experiment on it because it usually keep hidden by the cloud provider. So sometimes a lot of time you need to over positioning your system to meet our requirement. And in the next step, we want to extend this system to the IoT. So as I mentioned that, okay, we have latency tolerant and latency sensitive, and then we want to deploy it across 8 cloud. To the cloud, we're gonna have a latency tolerant service because the cloud is usually cheaper, and in the air we deploy the latency sensitive. So with the OS, you can imagine that we want to develop everything become a class, and we want to keep the thing the same to the cloud. So we don't want to go like, okay, here we want to secure shell to the cloud, secure shell to the edge, and deploy something. That is a tedious task and a lot of work. And so with OS, we want to have like a new layer of abstraction that work across edge and the cloud. That okay, we basically developer just need to describe the intent. Okay, this service we want to deploy it on the cloud. This service we want to deploy it on the edge, and everything should like magically happen like that. So to do that, we create a new architecture. We give a new name as a edge. We work as an implementation name. The OS IoT is the concept. So and you can see that the idea is pretty much the same. That okay, we have a package manager that accept the class or the deployment package, and it go to the cloud or like multiple edge server, and we have multiple components that do pretty much the same, but we have one thing more that we call as a messaging infrastructure. So idea behind it is that so now if the system span on edge and cloud, the communication between the cloud and edge is not like straightforward because in the cloud we usually have a multiple layer of like firewall, router, private network. So it's not like easy to do if you do it by like fast or like by hand. Everything becomes like much more complicated, and then you need to maintain a lot of like multiple service. So, but we want to abstract that. We want to say that okay, you develop multiple class, and if the one class uses another class, it should behind the scene like generate the network message across edge and cloud like transparently. So, and when you deploy one package, one thing that you can see is that it generates the class runtime, which is happen across edge and cloud, and with the single class that you mix up between the latency tolerant and latency sensitive. It basically you can deploy multiple class runtime across edge and cloud, and everything just coordinate efficiently. So, and then we upgrade the class runtime. Like it's not just LTAP. So now we have consistency that we not need to maintain. But I will talk about it in the next slide. So you can see that it basically the same mapping that as a previous LTAC template. We have a function, it's gonna be deployed in the logic engine as a function container. And then we have the middle component that we call as an object data grid manager that connect between the data that is an attribute in the class to the storage. And we have the messaging infrastructure that handle the cross-cluster communication. So to enforce SLA, so SLA and non-federal requirement, it pretty much the same, but we need to rename it for some like paper writing reason. So we have the availability to enforce that. Now we not just a single cluster anymore. So we have a edge cloud, or maybe we have multiple edge as well. So to preserve availability, so we need to calculate, okay, how many availability on each location that we require to meet the target goal, and then we just pick up the number of replica across all of the location that we have, like across, like let's say we have like 1, 8, and 3 like let's say 2 8 and 1 cloud. So, and then we calculate that, okay, to meet the 99.9%, you need 2 locations. So it can be like 1 8 and 1 cloud server. And to meet the consistency guarantee, so the thing is, as I mentioned, that when you deploy a system across edge and cloud, it can have an asynchronous because of a network partition problem. And this problem is not really easy to solve because there is a problem of consistency and availability at the same time. So the thing is, ideally you want the system to be operate without stop, and even though there is a network partition happen, you want them to operate. But it is not simple like that, because sometimes your application is you need to maintain the consistency. Like let's say that, okay, you update some data on the edge record. You want to make sure that the cloud also see the same data immediately. And a lot of times, things you cannot communicate with the cloud. So you know that it's impossible to keep the consistency when there is a network partition. So because of that, you need to sacrifice the availability to meet the consistency. So now consistency and availability is getting conflict. So there is a multiple option that you need to choose based on your requirement. So in the traditional way, so if you need to do manual configuration and meet all this, you need to understand deeper logic of how the trade-off between consistency and availability is. But we want to provide a higher abstraction that, okay, so you have an application that you need to make sure that edge and cloud see the same state all the time. So you say that consistency requirement is strong. And sometimes that, okay, you see that, okay, application is okay to have a little bit of asynchronous, but you want it to be like bound in the time. So we call it as a bound slowness with some number that we give it to the system. And the last is you not really care like how long it's gonna take for synchronous between the edge and cloud happen. You want the system to be eventually convert to the same state, but you don't care much about like how long it takes. But what you care is, so when the client writes something to the data, let's say client could be like, one function that you deploy in the cloud or you deploy in the edge. When you write something, you want the client to see the same data on the single location, but you don't care about like, okay, cloud gonna see the same or not. So you call it as a read your write. And to do that, we just deploy with a different kind of consensus algorithm. So, and lastly, throughput guarantee. So basically, it's going to come up to the same as we done before in the LTAP enforcement. That okay, we have the function deployed in the edge and the cloud, and then we have the monitoring system that measure like, okay, how much it do now and how much resource that it need to be readjust and deploy with the new under a minimum requirement that we define. So, and we improve that. We believe that the productivity is going to be improved by a lot, because it's not just about the single system anymore, and it's about like edge and cloud, which complexity light up like sharply. So we want to see that, okay, how well the productivity is in this system. So we deploy the system that we call real-time inventory management. So you can look into the more detail in my dissertation. But in this system, we implement it with fast and edge river, and we can see that with remove the logic of like manual communication between function and manual the state fragment, we can reduce the code by around 45%. But more impressively, the configuration file, since okay, if we deploy it with the fast or like Knative, or we have like much more configuration file to deploy like storage and everything, and like how to invoke the function, how to map the function because edge and cloud. So the number of configuration is like much compared to the edge river that you just deploy it as a class and then you just describe what is your intention as the SLA interface. So the number can go up to like 90% reduction in terms of line of code of the configuration file. So, and we not just stop that, we also did with the human study, and a lot of our audience in this room already participate in this study as well. So in this study, in each participant, we give them the tutorial with quiz and programming task to do with both fast and OS, which is 8 weaver in this case. So in terms of quiz score, we found that most of people they say they grade themselves that how much they're familiar with the cloud. So we have like 3 levels, that unfamiliar, basic, and competent. We actually have 2 more. I forget the name, but no one say that they are expert in this cloud field. So that's why we have only 3. And one thing that we can see that okay, all of the across 3 participants, the participant in 3 level of competency, they have a bit more score in the 8 weaver, which is kind of say that it is like easy to understand because since they are not know much about cloud, but they know a bit of the programming and they know a bit of OOP. So with 8 weaver, they can at least understand something that is like based on the OOP.
And that's just with 15 minutes of tutorial.
Yes, I think the tutorial time is a little bit dynamic because we have a mixing between online participant that and offline participant. So in the online participant, we kind of pick the time of the tutorial, but on the offline, people can just do it, take much time as they want. So, and we also did the programming task. So unfortunately, not all of them can do both tasks in our given time. So there is only some participants that can complete both. But to make the thing fair, because we know that if they start one first or another last, the one that they start first is going to be take longer. So we just like capture the time that they can do both of them. And given that, we can see that they complete 8 weaver faster in 31%. And I manually grading the how well they do in each both platform, and the score is kind of like roughly the same. So you can see that the productivity is go much around 30% higher, while the quality of the implementation is roughly the same. So and next we do the more system experiment. So we deploy the system across edge and cloud. So in cloud we deploy as a 3 server in Communion Cloud, and in the edge we deploy 1 server. But since the 1 server in the Communion Cloud is quite big, we want to simulate the edge, emulate the edge. So we use Kubernetes that we call as a KTD, which is the tool that help us to deploy the K3S, which is a more lightweight Kubernetes that designed for the edge. So we use it to deploy 3 8 server within single server. And we implement it with both Java and Rust. So in the control plane, we use Java, and the data plane, something like ODGM, we use Rust that is yield higher performance. And in this experiment, we only that I'm gonna show you, there is only 1 workload that is a JSON analysis. It's gonna label as an update. So in my dissertation, there is a much more experiment that is like more variety of the workload. But in the experiment that I want to show you, there is like only 1 workload. So I just report here for simplicity. So first of all, so we want to see like how well it can enforce the SLA, including consistency and availability. So when you deploy the consistency, you're gonna have a multiple options. You have a strong consistency, bound soundness with a multiple number of number of maximum soundness that you want to achieve, and then we have a lead your right. And the top part is the number of the soundness. So you can see that it can meet the requirement regarding of how many number of the total active object. So and even though it can do better, but if we say that it's gonna meet it in the 10 seconds, it's going to achieve in a bit lower than 10 to optimize to the automatic performance. And so, and the bottom part is the write latency. So write latency is mean that, okay, when you want to update the state, so you need to use some API that provided by, let's say in the normal case, you use database. So you want to write something to the database, you call the API to the database, and database gonna do something and return back to you. And I want to capture like how long it takes for database to do something and return back to you with different kind of the consensus protocol that we use. So since in this work, we use a LAF as a storm consistency protocol. So in LAF, you can imagine that to make sure that all core and cow see the same value, it need to block and wait until everything convert to the same state. And now you can see that, okay, even though we can reduce down to the stallness to very, very low, it can be 0. But and here the trade-off that we got is the write latency. So which is obviously that is something that people in the field that already know. But what is implicit is, okay, so basically everything now is just like single line of a YAML file. So you can just tweak this trade-off by just like change the configuration file and add the class level vulnerability, because sometimes this you can achieve at the whole database level. So basically you need to configure database is, okay, here, this database is store consistency, this database is weak consistency, but here you can do it at the class level granularity. That like you can imagine that in one application you can have multiple class, and in each class you can have a different kind of consistency guarantee. And you can see that we have a 2 column that is the availability requirement, and one is availability of 99.9, and we want to go a little bit more aggressive. We want to ask them, okay, can it give me the availability of 99 like 0.9999, like have an 9 number of 9. So and there is a little bit hard to see, but there is a number notation here that is like how many replica it need to meet this availability. And we can see that here we need allow 3, and here we need allow 9. So we didn't test it like with the experiment, but we this is like we can see that, okay, we can trade off with like by just changing the number.
What was BS in that?
Ball stallness.
Oh,
About the stallness.
and then 3S means?
TS?
I mean, BS-3S.
Oh, 3
3
seconds.
seconds. Okay.
So the next is we want to see like how adaptability of the system is like given if we have some kind of like network partition. So you can imagine that, okay, the link between it and cloud getting down. So what's gonna happen to the system? So in this case, we can configure in the way that, okay, we want one function to run on the cloud. Like if there is nothing happen, we want it to run on the cloud. And if something happen, we want it to run in the edge. So, and normal at the first in the blue line, we can see that it is just run everything on the cloud and nothing happen on the edge. And in the yellow part, there is the time that there is network partitioning happen. So there is the gap time that for the system to be like detect and aware of there is something wrong with the network, and then it switch back to use the local invocation. And we can see that, okay, we have two baseline, that is the read your write with the read your write with the throughput guarantee. And it's hard to see here, but the read your write with the throughput guarantee can sustain more stable performance. So, and when the network partition go out, you can see that everything just go back to the normal operation. And you can see that the detection and restoration it take not too long. It usually like allow 10 seconds to detect the system go wrong, and allow 5 seconds to converge back to the normal operation. So, and after we implement everything, so okay, we have something that seems to be useful. We want to know like how well we can like commercialize this. So we joined the I-call program that I already talked about it in the beginning. So we have done interview 101 interview with around 30 minutes each from 86 company. And we use the adaptive question based on the interview role and domain. So the goal is we want to identify and quantify the pain point and expectation for them. So what is the main problem that they usually face, and what is the expectation that they want to find a solution out of it. And the next is we also try to see that, okay, what is the opportunity for us to go into that domain and offer our solution for them to use. So we have two plot here. That is in the left side is a pain category, and on the right side is the expectation, what they're gonna want to get out of the solution, like what solution that they want to, or what is the criteria they want to see from the solution. So in the pain, we can see that they have a top three. That is a deployment, like so basically deployment is the difficult thing for them. And onboarding, so learning, have a new high to learn the thing is take a lot of time. They want to optimize this to be to have people onboarding faster. And then also talk about the complexity that okay, the system is really complex and it's hard to use. But some of them also talking about the serverless problem and security, blah blah. And the next part is the expectation. So most of them they want to improve like the productivity, of course, like they want to work faster, and then like to work faster. Sometimes it's not in the form of productivity; it comes in the form of the automation. So they don't want to work anymore. So they want to something to do it for them, and then we have a onboarding. And we can see that the pain point expectation is kind of mapping to the OS technical capability, and something like deployment productivity onboarding is mapped to the unified abstraction, and deployment maintainability and automation is mapped to the declarative LSR or SLA. And this is unfortunately we doesn't have much of IoT domain. But some of them also mentioned that, okay, the problem of deploy across account also one of the main concern, but we don't have much data point here. So, and we also developed the business model canvas over the time. So in case you don't know, it is the tool that helps you to shape your thinking, like how you can build the business. So, and if you don't aware of this, I can briefly just focus on the three aspects of the business model canvas. So first of all, do the customer want it? So which is the kind of the first thing you need to think of when you want to develop the new product or the new like company. So do you have a customer that really want your system? And we found that okay, there is so many like developers that want to improve productivity. A lot of them want to improve the onboarding time by reducing the complexity of the system, and some of them also want to automate the system and reducing the manual saving time. So it kind of like validate that okay, we have a lot of customers that wanting it, and then is this whole thing is financially sustainable. So, and you can see that OS or OS IoT is basically kind of follow along the same line of the cloud service model. And we can see that with the value proposition that we can give to the customer, there is a lot of money that they can save by just simply like work faster or like have some automation. And that is the cost cut. We can build up the pricing model, and it's definitely sustain our the cloud service. And last, can we build and deliver it? So this is something that is a gap between what we have right now and what we can achieve as a full-on company. So there is a like technical gap and then a commercialization gap. So technical gap is okay, what is the required feature? And there is a commercializing gap, like, okay, we need some partner, we need some fundraising, we need more manpower. And there is a more detail of this statistical model in my dissertation. You can check on that. So, and that's pretty much like everything. So let's conclude it here. So there is a problem on the cloud development right now. That is when you want to work in the serverless model, there is a fragment abstraction like computation, state, and workflow. And if you want to fine tune it, you need to do manual fine tuning. And the deployment is a hot end account is quite complicated. So we developed a solution that called OAS that unify the computation, state, and the workflow. And they also have a declarative NS non-functional requirement enforcement with the cloud extension. So as you see my the evaluation, it can reduce up to 44.5 line of code reduction and can help developer develop 31% faster. And we also validate the business model in the NWebI core program. And we can see that the one customer segment that we can target as a first start of if we want to build a startup is the SME or startup segment. And as for the future work, there is a technical gap if we want to go forward to commercialization of the system. One is the platform hardening, since our platform right now is proof of concept, which is available on the GitHub. I will show in the next slide. And next is the ecosystem integration, because when we want to develop something, it's not just about the like your code. You need to integrate with a lot of like tools. So we need to expand the ecosystem to help up development is more smoother. And then next is we can see that right now, if we talk about automation, it cannot go much far from like agentic AI, which we can use LM that become like trending right now. And last is the security concern that most of the enterprise interviewee, they're talking about the security, reliability, or compliance concern that, okay, if we want to go in that field, we need to do the security hardening. And all right, that is everything. Thank you for your attention. In here, we have two short code project and two of my main publication. And for the whole entire dissertation, there is two more that is already public. And there is a few, one more that is currently on the decision. All right, thank you.
All right, thank you very much. Very good presentation. I mean, this is in my opinion. So, any questions from the committee? Online people, okay. How about from the committees attending online? Dr. Song Fu.
Hi, it's a very good presentation. So a lot of illustrations. So I have several questions. So you're designing like an object that service infrastructure. So do you have any assumption about the objects? are they like independent, or there are some dependencies among these objects? So what's the assumption do you have?
Yes, there is it can have a dependence between objects. So if there is like, let's say that we have a object 1 and want to call to the object 2, so it can just simply like use the API to like to call like function basically, and then the hood is gonna generate the RPC call. I'm not sure if that is like dependent in functionality or like system optimization, but there is dependency between them.
Yeah, so if the objects are independent, it's relatively easy to manage, like they're using the function in a system already, and also probably the resource management is easier. But if there are interdependencies among the objects, and also probably I saw you have a DAG to represent some of the functions, so probably that DAG may be very complex, so that resource management may be a big problem.
Yes. So the resource guarantee, like let's say like throughput or ability, is at the function level. But when we have a DAG, ideally we can extend the NFI enforcement to the workflow that I didn't present it in case people didn't understand what I'm talking about. But in my dissertation, there is the abstraction that work on the workflow level. So, and since it makes things much more complex, so I just leave it as the first version or the first chapter, not first chapter, like it's a third chapter, but it's like my main work. But for the remaining work, like OS NFI enforcement and OS IoT, I'm not like touching on that subject deeply because it's like kind of less of the complexity by a lot.
Yeah, so I guess like for the example you showed in your presentation, also dissertation, and also the results you showed for the performance evaluation, so they are independent objects, right?
Yes.
Okay, I just want to clarify. Another thing is I saw you study the availability and also consistency as well, and then you also look at the throughput as a performance metric. So did you touch anything about the resource management for your system, like how to allocate resources, how to make it elastic, or anything touching like resource scheduler manager?
Since we use the Knative as the abstraction, like fast engine, like put it in that way. So we touch it at like high level. High level means that okay, we know that this function needs like file replica, so we just use the Knative API to just ask it to reserve a file replica, but we not like reserve it at like physical level, like mapping to the machine like that.
Okay, got it. Some questions about your slides, and so you have present some results on using non-functional requirement enforcement and see the latency. Probably it's at page 23. So are there any other work looking at the non-function requirement, and then what's their performance?
Yes. So there is a lot of work that trying to achieve, like they usually call as a QoS, but we
Right.
say that non-functional requirement is QoS plus like constraint. So yes, there is a lot of work, and we didn't claim that we like invited the mechanism to I try to find the slide.
I think it's 23.
23, yes. So we didn't claim that okay, we use this mechanism to enforce the throughput and latency, like just inviting in this work, but like we just building the platform that it can streamline the the requirement from a user to be the actual deployment, but the mechanism is it not like it not invited by on this work. We didn't invite new thing.
Okay. Just want to see like if there's some other work, probably better to.
There is a lot of work that try to like optimizing the system for target QoS.
Okay. Next page, please. So for the availability test, you emulated some failures.
Yes.
So what type of force you inject to the system, and also to where you inject that force?
Yes. So since we deploy everything as a container inside Kubernetes, so basically we just kind of terminate the container like every like randomly terminate the not randomly terminate. In every single container, we say that every 3 minutes it's going to get terminate and respawn by automatic Kubernetes thing. So every single pod in the system gonna get terminate. Every but when it's getting random. Sorry, I think I used the wrong word. It's not like it's not like every 3 minutes, but it's more like randomly. But the medium, the average is 3 minutes.
Okay, so probably it's a more coarse grain for to add it to the system. So probably you may look at some finer grains, like inject the force to the different components in your system and see how it works.
Yes.
One more question is about like page 30. You have a right, page 30. Right. So here you have a y-axis. It's a count. What does it mean counts? I just want to interpret.
Oh, so it's a line of code.
Y-axis.
Yeah, it's a count, but let's say that this is a line of code. It is a line of code, and this is a configuration line. Is so this the count is configuration.
How many lines?
It means frequency.
Yeah. So let's say in the fast it's like 600 line, and here is like allow. So this is like not like production level implementation. It's more like proof of concept.
Okay.
So line may be like lower than like normal expectation.
Okay. All right. And also for this scenario, you have like feeders from the different like sensors. Because your system is an object, based object as a service. So how you convert those, inputs from the different sensors into objects? Any examples like?
So basically, so in normal case, the data from this sensor is gonna be sent it to the some kind of like messaging fabric. We usually know as like MQTT broker.
Mm-hmm.
So, and when it go to the MQTT broker or the message fabric, we can have some connect it to the fast infrastructure that to invoke the function. And we also do the same for the OS. So basically, just invoke the one method of the object.
Okay. Just want to see like how you can implement on your OA.
Yeah, I think
AS
I have like
system.
more system design. So basically, here is how we design this previous diagram with the fast, and this is how we design the system with OS. So we design as a multiple class connect together, and they have a method consume. So we can configure the feed manager that could be like AWS LT call to call this method. Like basically, let's say that okay, if it come with like message queue, ask it to trigger this consume.
Okay, so do you have an object for each input? Just for each feed you have to the system, you have one object?
In this case, it's like we have one object per class.
Okay.
So there is multiple way to do it. Like we can like in OOP, so we can have like multiple objects to do the thing independently, or like one object to just do everything. So like singleton or like something like that. So there is multiple way to do it. But in this case, it's just like one object per each consumer type. And
yeah, the reason I ask is because like for some inputs, their data processing may take more time, so we use more resources. So I'm not quite sure. So probably for those heavy tasks, probably have create multiple objects to process it, may balance the load, improve the performance. That's just my thought.
So I mean, so even though it take more time, but in the end, when we want to get to the deployment, it just like go to different class runtime. So like this is one class, and when it deploy, it just deploy to the different class runtime, and each class runtime just optimize itself. I mean, it use class runtime manager to optimize, but each class runtime is optimized independently. So even though there is a different kind of workload behavior, but they are like completely separate.
Okay. Yeah. That's right. All right. Thank you.
Anyone have a question?
Yeah, I think from online, still we have Dr. Dinh Nguyen.
Thank you. It's a very good presentation. I just have one consideration about productivity in deployment. So you're saying that OAS or the object abstraction actually have simplifies the complications of deploying the application. Do you have? But it seems to me like is it just like a claim? Do you have any data to prove the claim? Like any experiment showing that OAS actually help you to resolve?
Yes. Yeah, this is a deployment productivity that we have done the work together. So okay, we have like 3 class of the application, and then we see one. So to deploy the system, we want to meet some specific number of SLA or SLO. So in here, like we have a specific target of the throughput, and we see that okay, if we want to do it manually, so we need to do multiple line of fine tuning. So like let's say we can just start by 1. And we see that okay, this is what we got as a system like in 1 pod. So we need to like calculate how many pods that we want to meet to this target. So and we find that it take around like 7 times to get like minimum number to meet the 10,000 requests per second. But compared to like Knative or like manually fine tuning, we can see that okay, we use Upalaga and then we just define it and it just somehow converging to this number without do the manually deployment.
Oh, I see. So basically, the point here that by providing the SLA, you allow the developers to achieve their performance or to enforce all the constraints based on SLA instead of having them to do the manual tuning, which can result multiple rounds of refinement if they haven't reached the requirement yet.
Yes, thank you.
Okay. Yeah, I think yeah, that's it. Very good presentation. Thank you.
Dr. Tong.
Your work is mentioned as object as a service. So could you give a typical application for this kind of service oriented?
There is so many case study that we have done and presented it on the paper. So I think one of the simplest one that is like real-time modeling system. So you can imagine that okay, if you need to do it, okay, I think
So
wrong one.
let me ask this question more clearly.
Okay.
Initially, Dr. Fu asked you what is the object, right?
Okay.
So could you just give this typical application scenario? Just give the example. What is the specific object you will provide as a service, and then how to use this object service?
So
One example is enough.
yeah. So okay, let's say counter. So you want to have like a service that is like counting the number of like let's say user session or something. And so if you want to deploy with a fast, so you need to have a function and then have a Redis database or whatever database that you need to keep the counting state. But when you deploy as an object, so you can write a class and then you have a number as an attribute. So and then you have a one method to update the counting the session, like let's say one method is increased, another method is decreased. So and then you just deploy this class. And behind the scene on the OS system, it will deploy the storage, deploy the function, and connect them together. So and then in the manifest file, you don't need to configure like okay how to connect to the storage. What is the what we call credential parameter that you need to connect to the storage, something like that.
So Do you have, you have evaluate your experimental result? This is all of the results based on the service request the trees of the real life benchmark. So you evaluate, for example, you submit, you calculate the throughput of your service, right? So the throughput is they need to process the specific number of the requests from user, right?
Yeah.
This is the request, is the real life request, because I see the experimental platform, including the TACC, the 3 servers in the TACC. So for example, the request, do you have the real life application to send that kind of request, like this server, the cloud server to process, or you just use some trees to simulate to get the features of all of the requests and artificially generate such kind of request by yourself? I would like to know the application benchmark.
Oh, so I'm not sure if I answer you correctly, but let me explain. Let me try to answer it. So I from my understand, you asking if how I generate the workload, right? So yes, so there is okay, given like I guess because there is like multiple experiment, I'm not sure. But let's assume the where go. In like let's say in this experiment, so basically if I recall correctly, this one is like JSON analysis.
Yeah, you
which-
mentioned the
Oh no, there is a tree.
data intensive, the compute intensive. This is kind of application, the workload running on.
Yeah.
That. So, but I would like to know this workload is real life the workload based on some benchmark, or you just visually generate such kind of things. The request based on some maybe some trees from industry is the productions
yeah.
They have some trees from industry. You just based on the trees to simulate.
So in this case, we use static, like we try to like simulate the bursty workload. So we not like we just want to test the worst case scenario. That is like what if there is bursty, like so basically bursty is mean that okay, there is like some time the workload really low and just go up really high and it go down, go up like that. So it's not like real
The
trend.
request is the real application, right?
Request?
Real application.
When you say real, you mean
Realistic.
Realistic.
so, like get it from real or like data set or something. Like let's say they have some data set that have a real
So,
set on the.
so for example, if you run a model, for example, the application, this is the real software will run on that. For example, you have the function as service, right? What is specific function? The function maybe can be currently is inference. The deep learning inference is commonly used a software, right? So this function. We just like give the input data. Okay, like predicts the results. So this is a function you build up in the server and you send the request. This you give the really the input data would like this function to produce output data. This kind of the application is the relatives. At least this is the real application. And then if this is application is widely used, then we see this realistic of the real life application. So this is based on the how your we can use it to just platform.
I think if I recall correctly, the compute intensive is image processing, if I recall correctly, and data intensive is the I think this is image resizing and this is a video processing. And this is the JSON analysis, like load the JSON from the database. So it is some.
So your evaluation benchmark is the raw application, right?
It use the same pattern with the real application, but I implementing it to just use in the
You simplify that. For
Yeah,
example,
simplify.
we have the function. We also have a kernel. So this is kernel, not the GPU's kernel. This is the kernel has the codelet. This is a critical code in this function. So we can use this to simplify the real life application. So this is the real application, but this is simplified, right?
Yes, it's in real. Like we send the real message to have it run like real, like what it's supposed to do, and then you get the result back. Yes.
Okay, thank you. I think overall you present your approach for the OAAS. This is
Yes.
the high levels the framework you propose for serverless computing. I think the entire work is good. And last question is so in the outline.
Yes.
So you have the chapter 3 to 4, chapter 5, chapter 6. You deliver the two main papers. One is the TC, another is the SOC. So which work is corresponding to which paper?
So there is actually 4 papers that already published. I mean, 2 conference paper, 1 journal, 2 journal. Yeah, 2 journal is on the OS. Another one, I mean, is chapter 3, and 1 paper is on chapter 4. And there is one abstract for like tutorial.
Wait. So you have the SOC paper based on which work?
The 3.
Okay.
No, sorry, it's a 4. SOC is 4, and TA, like transaction on computing, is 3.
Okay, that's fine.
But not computing computer, but yeah.
Transaction on computers, and I think.
I know this is a top journal in your system.
Yeah, it take me a year and a half to get to the transaction on computers. So it may be weird that I just get topic like a few days ago, but it actually like first work.
I think you did a good job for your dissertation. Okay, you finished all of the dissertation and can present it's clear, and also you have the publication, the solid research work, the good publication to support your dissertation. I think it's.
Yeah, thank you.
So yeah, I think it's my turn. So I think I had enough number of years to ask enough questions. So but just to ask something, I can ask one question. Just go a little bit down slide 34. And so I will have one question here. But before that, maybe you can turn off the recording. I should have told it a little bit earlier. And then back to your question, Dr. Khan, about the application, the use case that you were looking for. I think one very obvious use case, I know a high-level use case, like